Okay, good morning together, and welcome to the second lecture in control and perception in networked and automated vehicles. And as in every lecture, I will show you this slide for some seconds, and then we will start the lecture. So this is for the privacy policy. I hope you have read it now. So we can go to today's lecture. And today, I would like to start with a diagnostic test. You should be able to open the link or to use the barcode to open the link. Patrick, maybe you could post the link in the chat. Okay, now you have also the link in the chat. To the test. It's here as you see. So, yeah. We will do it together. So please start filling in your name, study program, semester in master program, and then we will start with the survey. So the idea of this survey is to know your knowledge in this topic, to be able for me to adapt the lecture to your needs and to your knowledge. So please do it right. So I'll explain it very shortly. So we have just 3 possibilities to answer: no knowledge, good, and very good. People tend usually to say no knowledge if they have forgotten the concept. So please put good if you know anything. So please fill in your knowledge in the single topics. If you have questions, just speak. Now we are 30. I am twice in as Vortrag and as myself. We have also Patrick, so 3. And somebody is also twice in. So I don't know why you are twice in.
Yeah, that's me, because I'm sorry. Wait a second.
Yeah, it's because you're twice in. So maybe once for the microphone, and the other one is for other things.
Okay, so I'm back. No, I have two devices because my microphone doesn't work on the one on my notebook. So, but I like to use it to see your lecture, to have a better view on it. And I'm using my smartphone for the microphone usage. So that's why I'm in with two devices.
Okay, we have to think for the number of participants to subtract 4, right, Patrick? Okay, we have 26 today. And if I look at the results, 3 people have already participated in this survey. And now we have 15, 16. So it's growing. So take your time to understand the questions and to answer them. 17, so it's automatically updating. This is good. So I'm expecting at least 26. At 26, we will stop. Okay, nice. We have 24 answers. So I hope at least 2 are still doing the survey and are with us. So at this point, I would say if you don't have questions about the survey, now we have one more. So if you have questions, just turn on your microphone. Else, I would say I will analyze the results and present you next week. But for today, I would like to proceed with the lecture. Yeah. So we had the diagnostic tests, and now I would like to present the lab in some more details because it is very related to this lecture. So I should be able to switch slides. I'm trying to do it. Yeah, now it's working. So at the beginning of each part or each subpart the lecture, you will find some literature from other groups and also from our group. And because the lab is our work, so you see here literature from us. So here are 3 papers written by our group, and Patrick and me are authors of all 3 papers. So you can look at these papers if you want to know more about the lab, more than we can teach in this class. So this is an overview of the lab. On the left, you see simulation. Of course, you can test your ideas in simulation, but it's not very exciting. It's more exciting to see what you have done in reality, somehow physical and driving. So that's why we built the lab. The idea is to see your ideas developing into reality. And of course, real world experiments are more exciting, but it's costly. And if you have a number of agents, in this case vehicles, it is not possible for a university to be able to conduct such huge tests. So for us and for you students, it is good to see the ideas, to see the network. So this is why we built the lab. Now I would like to go to the next slide. So here we see the main features of the lab. So the features, or the main features, are 3. The first one is to be open. So and at the same time to be remotely accessible, and especially now during the Corona crisis, it's valuable if you can work from home. So for the open source policy, we made the code open on GitHub. It's already uploaded on GitHub. Our construction plans for the vehicles, for example, are also open, so you can download it and rebuild the vehicles. Our documentation is also completely open. You can find everything online. We published the code plans and documentation during working on the lab, and we are still updating it. The remote access to the lab is under construction. You will test maybe version 2 of the remote access, but it is not the final remote access. So you will also work from home, first with the simulation of the lab, upload the results. We will tell you how, and we will conduct the tests here for you, send the data and also a video to see your ideas developing into reality. And you can see your results, your videos. And if you are happy with the results, you're done. If not, maybe we can give you a second chance to re-upload your code, and we could reconduct the experiment and again upload the results for you. So the second main feature is the rapid algorithm prototyping. So for this, we have built 20 network model scale vehicles. We call them mu cars. I think now 16 to 18, I'm not really sure, in action in the lab. Patrick, how many do we have now?
Yeah, 18 at the moment.
18, okay. So 2 are pending. Yeah, and you can test your algorithms centralized on a central computer or distributed on different computers. This is what we are going to learn in this lecture. So here we have the main computer of the lab. We call it the lab control center, or let's say the software running on it. It's called the lab control center. Yeah, it is connected to the lab camera. The lab camera yeah, detects the positions and orientations of the vehicles. And also we have a router which communicates between the vehicles and the computers. And we have also single computers for each vehicle. So each vehicle has its own computing unit to be able to, let's say, to simulate the reality that each vehicle has its own computation units. So what else? Here you see the remote access. Multiple users will be able to use the simulation at the same time, and yeah, we will have access control to the real lab. So the third main feature is the hierarchical service-oriented architecture. Maybe the computer scientists between you know more about service orientation, or in general about software architectures. So service orientation is a modern concept in software architectures. And in the lab, yeah, we added the hierarchical aspect to it, to be able to to have the different abstraction levels on different computation units. So we have a microcontroller, as maybe you know from the BSP in the second or third term in computer science. A mid-level also mounted on the vehicle. It is a Raspberry Pi Zero. Our low-level microcontroller is an Atemega. And the high-level computations, the more complicated computations, let's say the optimization-based algorithms, run on the high-level computers, on the external computers, which are logically on the vehicles, but physically separated from the vehicles. Also due to the weight, because we cannot have them on the vehicles. So what also belongs to that service orientation is a middleware for data exchange and synchronization. And for this, we use DDS, Data Distribution Service. It's a modern protocol for distributed data exchange and synchronization. Do you have questions till now? I am seeing new messages in the chat. Maybe if something is relevant, Patrick, to the lecture, you can mention it.
Yo, I will let you know.
Okay. So I continue. Here we see the logical architecture of the lab. So we divide the lab after the scheme, sense, plan, act, and also we define an infrastructure part where we set up the lab. So the sense, plan, act is the common concept in this field. So I will start explaining the infrastructure part, the setup. We have a scenario server where we define the test which should be run next. And what belongs also to the scenario server is the mission planning. So mission planning is, let's say, the next or the targets to drive to. For example, if you would start in driving in Aachen, the first thing you do is you do a mission planning. If you have just one goal, it is easy. You say, okay, I'm going to drive to Cologne, and my mission is to drive to Cologne. This is your mission. It could be more complicated. Think of, for example, packet delivery, where you have multiple goals. So what we add to the scenario server is simulation of passive traffic participants. So, for example, pedestrians, which we don't have in the lab. Of course, we could also use some vehicles to simulate pedestrians, but in general, we simulate what we don't have in the lab. We simulate as passive traffic participants. And also, of course, in the lab, we can add more vehicles than the 20 simulated vehicles we can add to the lab. So what belongs also to the infrastructure is a map. A map consists of 3 levels. A static map, like you know from Google Maps. If you open it on your smartphone, for example, you see just a static map, a road network. For example, if you would open it near Informatik Zentrum, you would see Aaronstraße and so on. And the second level is the dynamic map. So the dynamic map contains additionally traffic participants. For example, cars or also pedestrians. We save them in the dynamic map. Let's say it is an overlay of on the static map, and it is function of time. Additionally, we have the preview map, where we make predictions of the traffic participants, or where the traffic participants can store their predictions or their plan. Where are they going to go to? So these information are very essential to network and automated driving. So this is, let's say, the basic you can build on. These are the data you can, the inputs to your algorithms. So what we get here to be complete now from the scenario server is scenario, static map, and mission plan. So what we also have in the infrastructure is a module which adds errors and noises to the signals to be more realistic than just in the lab. So going to the sense part, we can divide it into two modules. So this modular architecture in the lab allows for fast replace of some modules. If you want to change anything in the lab, you don't have to change the whole lab. You just replace a module, and ideally it should work together with the other modules if you have considered the interfaces in the right way. So we have sensors. Sensors send sensor data to the perception, and the perception computes object data. So what I would like also to mention before continuing is that this architecture could be also for real autonomous driving or real network driving. It is not just for the lab. So what we are trying, or what we did in the lab is a simulation or a map of the reality. So in the result of the map is an environment model, a dynamic environment model, where we have the different traffic participants, the route map, and so on. So the result is a noisy and more real environment model. So this goes to a module named coordination. This is one core part of this lecture, to learn how to set up this coordination. Why do we need this coordination? Which schemes could you apply here to coordinate vehicles, and so on. So the result we save in a coupling graph, and then it goes to a decision-making module. The decision-making modules get also the environment model to be able to take decisions. And also, what I haven't mentioned, the decision-making sends also states and plans to the map, which will be stored in the dynamic map and in the preview map. So the plan in the preview and the states in the dynamic map. So what also belongs to the decision-making are mainly, in general, 4 modules. The routing, from the example I've taken, if you start in Aachen, you want to go to Cologne, then you have the mission plan. And the first thing you have to do on Google Maps is to say, calculate for me a route. So how should I get from Aachen to Cologne? If you're driving a passenger car, so you have to take the A4 and then change from, let's say, from a highway to other highway, and then to let's say motorways or Landstraße, and then to the city streets and so on. This is the route. What also we need to be able to get from Aachen to Cologne, but not on this horizon, is to take decisions on the behavior. A behavior could be to take over on the highway. So you don't want to drive the whole time on the right lane. You want also to, for example, overtake a truck and so on, and you have to take decision on your behavior. So do you, what next to do? So the next level is the trajectory. If you have taken a decision about the behavior, now I would like to take over the track. The trajectory is how to take over. So it is more specifically the X, Y, where you should be next in the next states. The orientation belongs also to the state, and also what's important in trajectory, the time. So be at position X, Y at time T. So if we have calculated or computed the X, Y, and orientation, and the time where when we should be there, we have to apply this to take action. And this is the control. Here, the control is also to act. Now we are going to speak about the actuators. But before that, I would like to speak about the result of the decision-making of the states and the plan. So the states and plan calculated by or computed by the decision-making should be also verified. Either are they, for example, deadlock-free? Are they safe? Are they efficient? So this is what we can decide using a verification. So we can decide to conduct a plan or not. If the verification module says, well, everything is fine, go ahead, then we apply the control inputs using the actuators. So the actuators, yeah, it depends on the level of detail you are working in. So if you are just interested in high level stuff, then you calculate or you compute a steering angle of the wheels and a position for the acceleration pedal or for the deceleration pedal, for the brake pedal. And that's all. And if you are interested in more, so you have to find or to apply these signals also down to the vehicle. So there are many control circuits in a vehicle, and yeah, in most cases they are hierarchical. So you calculate or you compute a steering angle, and to apply this steering angle, you have to go to more deep in the mechanical parts of the vehicle to be able to apply it. Or if you if you want to accelerate and push the acceleration pedal, then yeah, it depends if the car has a combustion engine or an electrical motor or whatever. So there are many things to control automatically during driving. It's not just the high level things we handle in this lecture, but we are not going to speak about low level. Low level doesn't mean it's not it's easy. Low level means just in the hierarchy. So sometimes, for example, to control a combustion engine to be efficient could have the same challenge as computing an optimal trajectory. Well, do you have questions till now? Well, I would continue. Okay, in PowerPoint, I would have here an animation, but we're using now PDF. It's no problem. I can explain it without the animation. So here we have the let's say the concept of the lecture and the application of it to the lab. We have the perception using sensors and sensor fusion, control and optimization for computing trajectory control and how to apply them to the actuators. We have here the network and distribution between agents, and here on the top we have the software architecture and testing concepts. So this, let's say, a picture of the content of this course. So the main part of this course is the network and distribution. Okay, maybe I should have taken the PowerPoint slides. I can switch now and hope that it's going to work also. It's working. Now we're saying the lab in action. I think we took a look at it in the last lecture, but again in this lecture with more participants. So this is what you hopefully are going to be able to do after taking this class. So I'm not going to explain the video again. So if you are interested in the explanation, go to the next lecture. Okay. So now we're moving to the next part. This is the chance. If you have questions, just raise your hand. We would be happy to answer your questions. Well, now I would like you to discuss in the groups. So Patrick has already divided you into groups and teams. What are groups and teams? Go to the last lecture, you will know it. So now I would like you to discuss about two questions. The first question is, which tasks do you perform during driving? If you have a driving license and maybe you have a car, so just think in detail about what you do to drive. Which tasks do you perform? If you're not a driver or you don't have a driving license and never took the steering, just think of a situation where you are the co-driver or sitting in the front seat, and think what the driver does to drive. And I would like you to suggest a definition of automated vehicles. So what you do during driving and what you would like to be replaced by a computer is more or less the automation of vehicles, and I would like to to suggest a definition of automated vehicles. Okay, now I am unmuted. So when we go back from the breakout sessions, we have also, or I have to unmute myself. So it is nice. So now we are again 30 participants. So we have 5 groups, and the 5 groups have discussed about the questions. So I would like now one person from each group to present your answer. So I have forgotten to tell you that you have to find one person to present your results. So the first one who will unmute his microphone or her microphone will be the representative of the group. So now somebody from group A.
Okay, so if nobody, I can try. Okay, for the first task, I think every driver have to do 3 things. For the first one is navigation, and for the second one is your control. And for navigation for a driver, I think you have to type your start point and end point and to navigate in the Google Map. And for the second one, perception, and you drive on the road and you observe the environment and the vehicles, the pedestrians, something like that. And for the last step is control, you steering, you braking and accelerating this, do some actions like that. And for the second task, I think the definition of the autonomous vehicle is also do this, can perform this task, these 3 tasks autonomously. Yeah, from the very beginning, the navigation, and you choose your navigation, the trajectory, and your routing. And the second one is your perception, and the last one is the control. And after the very beginning, and I think it's going to be a closed loop control, and you perceive and you control actuation, and then goes back.
Okay, it is a nice view. So now somebody from group B.
Yeah, so maybe I would do it because I wrote down the possible definition.
Yeah.
So for the first question we had, we grouped our answer into 3 subgroups, like sensor task, actor task, and plan task. And for censoring, we said something like satisfy the traffic rules by checking the road and the surrounding. And we are trying to keep in lane when we are driving. For the actor task, we try to operate the car, so actually drive it. And then we also, we need a route. So the third subgroup, planning, would be to find a route from my place to somewhere else. So that were like the tasks that we wrote down for question 1. And the definition for automated vehicles was a driverless vehicle that can sense, plan, and act on public roads with other participants and on its own, according to the traffic rules, and without a human being held responsible for the actions. It is really long, but yeah, we tried to put in everything.
This is your definition of automated vehicles.
Yeah.
Okay, nice.
Yeah.
Okay. Yeah. So we have a little bit different view on the topics. Now maybe somebody from group C.
Yeah, I will do it. So we made a general definition for automated driving. We said it's the automated data mining of the control input regarding the observed environment. And the observed environment includes the sound signals, light signals, traffic signs, and so on. And based on that information, the vehicle has to determine the control input like steering or acceleration and deceleration. And that was our definition for automated driving.
Okay, nice. This was group C, right? So now somebody from group D.
So we basically, for the first question, we only really looked at the control part of the driving task. So what we perceive and how we control the actuators that are, how our feet are actuators and our hands are actuators on the steering wheel or pedals. But we also said there are some other parts like planning the route that has to be taken into account that we do also during the driving task. Sometimes we let ourselves be distracted by other things like entertainment in the car, but during the driving task we shouldn't. Our definition was basically automated vehicles are vehicles that can take over predefined tasks for the driver and do them on their own, basically. But we limited it to predefined tasks because we didn't want to say the vehicle had to be completely automated to be an automated vehicle, but it could also be some very limited tasks that can be automated, like adaptive cruise control or something like that.
Okay, fine, thank you. So maybe now somebody from group E.
Yeah, I can present the things.
Yeah, please.
So for the first task, we said that the driver has to observe the street and do localization with the help of, for example, buildings or Google Maps. You have to control the car, and you have to predict the actions of others, for example, other cars or, I don't know, a train. We have to check the mirrors, so we also have to also move our head. But we also have to check for sounds, maybe if we near tracks of an emergency vehicle or near train station, then do we have to plan the trajectory of our car, read signs, respect the law. For example, we have to stop at traffic lights. And for the definition, we said that an autonomous car should take over all the action the driver would perform, like the task we mentioned above. And the driver is just an observer in this system.
So thank you. So I am proud of you. Maybe you don't need to have this lecture. So you already understand what is automated driving. But two things I would like to add to your discussions. One point, you assumed, or you are assuming that a driver should always be in the car. This is maybe not always the case. You can also think of cars without a driver inside. A car, for example, which goes shopping for you. And a second part, which is also the core part of this lecture, is the network, the connections between the vehicles. So I think this is what you will learn also in this lecture. So I will show you the, okay, first I have to to share my screen. Zoom. So you should now see the slides again. I don't know how can I get rid of this. Okay, we just continue. I can take care of the, okay, now it's it's gone. So we have here, let's say, yeah, it's not a definition, it's more decomposition of the driving tasks during driving. So in this book, it's a German book, Handbuch Fahrassistenzsysteme. So it is about driving assistance systems. They divide the driving tasks which we perform during driving into 3 levels. So they look just at the actions, not at the perception. So the first one is the navigation. It is the route planning and the routing. So the route planning is the static route you compute in Google Maps, for example, before you start driving, and during driving you get the commands continue on A4, change from A4 to I don't know, 66. Somehow the commands during driving. So the second level is the guidance. It is more to compute the next actions. It is more the trajectory planning and the interaction with the environments. Let's say it is like the next 100 meters, where you, for example, see, okay, a roundabout is coming. I have to reduce my speed to be able to stop at the roundabout, to look if a car is coming from the left side, to drive around the roundabout and to drive outside. So this is more the guidance. So the third level is the stabilization. It concerns longitudinal control and lateral control, and it is safety related. And the first safety systems or assistance systems were developed for stabilization, because if the car isn't stable, we don't need to speak about the guidance and navigation and to improve the feeling in the car if it is not stable on the road. So systems in this area are, for example, the electronic stability program. In German, you would say ASP. So this is a stability function for to stabilize vehicles, especially on curves. So in this lecture today and in these slides, I'm not going to go deep in details about driving tasks and about the single functions and so on. It is more to raise your awareness about these topics. So, yeah, if you think again about the lab architecture, you would see like a definition of the functions or of the modules you need for automated and networked driving. So now we have a definition of automated vehicles. Yeah, the bad news, there is no definition. There is no real definition about automated vehicles, and there are many definitions. But what is important for you, I think, is to know the background. And here is a book written by Professor Maura about autonomous driving. You can find the book in German and in English. If you are in the university network, so you get it for free from Springer or from Springer link. So just type the name of the book or the title of the book and the name of the author, and you will find it. So it is generally written not just for people with technical background. So if you would like some people without technical background to understand more autonomous driving, and if they are interested in this field, so maybe it is a good idea to make them a present and to give them this book. So in this book, and this is in my opinion also important to understand where the words come from we are dealing with. So the first point here is explaining where the word automobile comes from. So it is, maybe in the German word Kunstwort or artificial word, it is combined of two words from Greek and from Latin. So this sentence is taken from this book. When the car was invented, the formulation of automobile combining the Greek autos, and autos comes from self, personal, or independent. So it is in its origin, it includes the independent word, and the Latin word mobilis, mobile, and if you put the two words together, it is a self-mobile. It is already defined to be more or less automated. And if we look at the word autonomous, then we have nomos in the word. It comes from Greek, and it means human order or laws made by people. So what an autonomous system does is to conduct laws made by us. And if you think more deeply about autonomy, and also in the philosophy, it is the self-determination within a superordinate moral law. So it is also your autonomy, if you would also think about your autonomy. It is really interesting. Maybe if you are interested, you can read more about it in this book, or you can use also Google to find more about these definitions and concepts. So what we are doing, or what we are going to learn in this class, it is not just for street vehicles, or let's say for road vehicles. It is also general. You can apply it also to robotics. Or what we learn here, we have also taken it from robotics. So an autonomous vehicle, road vehicle, is also a robot, if you would like. So the next point you have also discussed, I don't remember exactly in which group. I remember a group was discussing about automated and autonomous. What is the difference between automated and autonomous? And some people don't agree on a definition of what is the difference between automated and autonomous. But some people say, okay, actually what we are doing is automation. The vehicles are automated and not autonomous. And if you take it precisely, then an autonomous vehicle, if you get in, it would, and you want to drive to the office, it drives to the beach. So an autonomous system decides by itself about the mission planning also. But in my definition here, I would rather say, also if I tell the vehicle to go for shopping or to drive me to the office, it is still autonomous. Of course, the mission planning level is still decided by me or by the algorithms I design. For example, if you would think about packet delivery. So mission planning is the point where you can also distinguish between automated and autonomous. And a second point, people could say, okay, autonomous system, it is more a closed system. Does it communicate? Does it cooperate? We should more speak about automated. And in my opinion, no. If you look at the definition of Kant, then we are, as human, also autonomous systems, but we communicate and we cooperate, or let's say we should. We don't do it every time we should, but basically we do it. So in my definition and in my opinion, we don't have to struggle about automated and autonomous. The goal is to have autonomous vehicles, and on the way we have the automated vehicles. So to be more precise about this topic, I'm going to present to you the levels of automation. So it is, again, I'm not going here to speak about details. It is just to raise your awareness about the topic, just to know how such topics are handled by big organizations. So to my knowledge, there are three, or for us also in Germany, there are three important organizations which give definitions of the levels of automation. The first one is from the Society of Automotive Engineers, SAE. So they define 6 levels. Level 0, let's say it is nothing. It is the car from 20 years ago. And level 1, to be very short, it is hands-on. So in level 1, you have to have your hands on the steering in the car. In level 5, you can take off your hands, but you have to still watch the road. In level 3, you can look away. For example, you can look at your mobile phone and type a message. In level 4, you can also turn off your mind and do something completely different. And in level 5, you don't need a steering wheel. Steering wheel is optional. So there are also further definitions from the National Highway Traffic Safety Administration of the US. And in Germany, we have also the BAST, Bundesanstalt für Straßenwesen, German Federal Highway Research Institute, they have also their definitions. But basically, all of them have more or less 5 levels. So if we look more deeply on the SAE, then yeah, I have taken this picture to illustrate it just in one slide. So on the left, we see the levels 0 to 5, and they are divided into two let's say again levels where the human driver monitors the road and where the automated system monitors the road. And yeah, in the column we see the steering and acceleration and deceleration. That means controlling the steering wheel and the acceleration and brake pedal. Who takes care of this part? Monitoring of driving environment. And okay, the third one is fallback when automation fails. So if the automation fails, who takes care about the vehicle to continue at least driving to a safe halt, for example? Yeah, and here we see in the fourth column the automated system is completely in control, and this is the case in full automation in level 5. So here, yeah, you can study this picture in more detail, look at it in more detail, but I would like here to give some examples. So if you look at the second row, you see here the driver and the system take care about the steering and acceleration and deceleration. And this is the case, for example, for cruise control systems or speed control. It is other word for cruise control. In German, people say Tempomat. So the car would keep a predefined speed which you put somehow in the car. It is more common on highway that people use it. So people say, okay, I'm going to the highway and I have a long distance to drive, and I don't want to always drive very fast on the Autobahn. So I decide for 120 kilometers per hour and tell the car, okay, take care of the acceleration and deceleration. And as a driver, I'm going to watch the road and to take care of if there are other traffic participants in the road. For example, if a vehicle is slower than my vehicle driving in front of me. So an extension of this cruise control is the adaptive cruise control. People say also ECC. It is nothing about adaptive control. It is just adapting the speed to consider vehicles in front of my vehicle. So the system senses not just the speed and controls it, but also the car in front of my car and adapt the speed to keep a distance between us. So in this case, I just have to control the vehicle to stay in the lane on the Autobahn, and the rest is done by the system. So if we go further, we can also go to level 2, where we have also somehow a lane keeping system. So I am not sticking to the word lane keeping, because if you go to different car manufacturers, you will hear different terms about lanes. So in some of them is lane keeping, just to warn the driver if the car is going to leave the lane. In other cars, it is the lane departure warning system. In other cars, it is the lane following system, and the lane following is more to stay in the lane, and it is more what should be here in this part. So the vehicle takes care of the speed of the car up front and keeps also the lane. This is what we have nowadays on in modern cars. So if you take some more euros in the hand and buy some more expensive car, you would get this system in the car, and on the highway you don't have to do anything. You have but to, of course, monitor the driving environment and do the fallback system, so that the car takes care of speed and of distance to the front car and of staying in the lane. But you are in charge of the system as a driver. You have to monitor the system. So in last year, I offered the student to drive with me in our chair vehicle, in our chair car. So maybe, Linus, you could turn off your microphone. Okay. Yeah. I offered the students to drive with me to see this system. We have a car in our chair which is able to fulfill these functions here. But now, due to the pandemic, I'm not going to offer to you. If you are still interested in it after this course, maybe in next summer, would it be able? You can contact me to see the system in action, to feel what you are going to develop or what you have developed. So now we are 4 minutes over time. I would say we stop here at this slide, and we continue in the next lecture. So we have still some slides about the introduction. I would like you to know some concepts before we go deep to the modeling, to the mathematical backgrounds, and where it will be, let's say, drier. So I would say see you next week. Thank you.